All right. Welcome back to the Lab 5 or Chapter 5 video for data mining with cluster analysis. Um, Basically, it's about cluster analysis, right? Uh, so in this section of the video, this particular lesson, we're now talking about more advanced techniques for business intelligence, but clustering is also used for predictive analytics, right? It's basically we're using the clustering technique or clustering analysis in this particular case to solve certain problems, but it could be used for both diagnostic, descriptive analytics as well as predictive analytics. So this is more of the quote unquote cool stuff, right? This is now we're getting into the more advanced stuff of analysis, the more advanced concepts of analysis. And right now, what we'll do is we're just going to use a simple package from R, a very simple package from R, to do the analysis for us. In this slide, we're going to cover basically um, what is cluster analysis. We're going to talk about partitioning using k-means clustering. And we're going to talk about clustering using hierarchical techniques. There's another form of clustering that's called, uh, instead of hierarchical, it's the other way. Oops, hold on a second. Hold on. Get this stuff going. So the one technique I'm not talking about here in terms of clustering is agglomerative clustering. So hierarchical clustering is basically when you start off with many clusters and you go to a few clusters. Agglomerative clustering is basically the opposite. It's where we start with one cluster and you break up into many. So that's the one we won't be discussing. Right now for today, we'll be discussing k-means and hierarchical techniques. All right, let us start with loading up our data. So there's two files you saw on Blackboard that I loaded up for Chapter 5 or Lab 5. And we're going to start off with using the bike stations locations one. So I already have that downloaded. Let's go ahead and grab it. Bike stations locations. Excellent. Let's just, oops. Looks like my R just went down. Open that up again. Okay, so I got this back up. So again, once again, I'll leave this name right now because I'll just copy from this just like we did before. Yes, I do have headings. No, I don't want strings as factors. In this case, I just have two columns of numbers anyway. Let me import it. And I have the data I want. From here, let's go ahead and look at the data just a little bit. I have the table open. Notice it's just two columns, latitude and longitude. You guys know what latitude and longitude are, right? Those are positions on a map. And this data set is basically the position of a bike stations or like the fictional data set, if you will, of bike stations in Washington, D.C., right? Any guys ever use those bike stations? I have in the city. I have, and it's basically used. I love it. I love using those bike sharing things. They're amazing. And all these different cities have it. DC has their own. So this is basically the data set that's supposed to represent that. All right. Now, we're doing this cluster analysis for the sake of what we call data mining. Now, technically, the definition is the process of working with large amounts of data to gather insights and find patterns. Now, in our case, we're not dealing with large amounts of data. We're dealing with a small amount of data, 244 rows, right? Yeah, 244 rows, and that's mostly for just so it's easier to explain, it's easier for everybody to work on their computer. The data does not need to include a responsive variable. What do we mean by responsive variable? When we did a regression analysis, right, we had independent variable or variables, but we had one dependent variable. That dependent variable counts as a responsive variable. Okay? When you have a situation like there's other kinds of, like for instance, if we start doing machine learning, classifier problems. Classifier problems, you train the model using some sort of training data, and you have, like for instance, your independent variables that you want to predict on a dependent variable. There's something being you're training the model to predict something explicitly. In this case, okay, you don't need to have a responsive variable every time. Clustering analysis is that sort of example. Clustering analysis, there is no responsive variable, right? The belief is that there's a relationship about the structure within the data itself, right? Within the data itself. The data itself will avail itself of some sort of structure or pattern without the need of any kind of responsive variable. All right, and that's what clustering analysis is. Now, what is clustering? It's very simple. It's just the concept of making groups out of data objects, right? That's all it pretty much is. Those groups, you want them to be very similar with one another. You want the data items in those separate groups to be very similar to one another, but you want those groups to be very different from one another. So that's the whole point of clustering. Clustering's objective is two things. Is to make groups so that the items within the groups are highly similar to one another, and to make groups so that one group is very different from the other group. All right, so a simple example right here is, imagine you have a dinner party in a rectangular room. This is a rectangular room right here. And all the guests don't want to congregate around the center. I don't know if you guys have gone to any kind of dinner party or hangout. Everybody's not in just one big massive circle talking to each other. All right. What happens is people break off into different groups based on different reasons, interests, what they're discussing, who finds who interesting, etc., etc. So if a party starts off like this, towards the end of the evening, it turns into little groups like this, right? Large party, not the small ones, intimate ones, but a large dinner party at a museum or something along those lines. So that's basically the concept of clustering. So clusters themselves are collections of points, obviously, from a multi-dimensional data set. Right now, we're looking at a two-dimensional example right here. Don't constrain your mind to that, right? There can be n amount of dimensions on this data when you're doing cluster analysis. Obviously, 2-dimension and up to 3-dimension we can visualize. After that, we can't, obviously. In this particular section, we're going to focus on the error between the data points and their central point within each group of clusters, right? That's basically the major measure used in cluster analysis. When we're working with linear regression, you will recall again that we had the response variable, right? And that is what we call supervised learning. Supervised learning. Cluster analysis, it does not have response variables. That is called unsupervised learning, right? In unsupervised learning, there's other ways to basically explain the relationship of the data between one another, right? In this dinner party example, right, the method would be to find a central point within each identifiable cluster, for example, here, here, here. And that would basically help identify for us where the cluster where the individual cluster is. Again, we explored two different types of clustering methods: partitioning and clustering. Partitioning and clustering. Now we're going to start off with partitioning using the k-means clustering algorithm. The objective of partitioning is basically requiring a set of points within the data and minimizing the distance or error from each data point to the specific location. So you basically are throwing some points, some central points into the data, okay? And you're basically calculating the error for each data point in your data to those central points, to the closest central point, right? And basically you're calculating the distances of all these data points to the closest central point. And the objective is to minimize that average distance, for overall for your whole data. Now, the whole concept of k-means, Parching method of k-means, it means placing centers at k locations in the observation space, right? The k basically here stands for some number, predefined number, that dictates how many central locations your data will have. That is what k means. That's where the k in the k-means comes from. So for example, if we were doing the k-means clustering analysis where k equals 3, we would be creating 3 clusters. We're going to be attempting to create 3 clusters in our data space. K-means, the algorithm for k-means, it iterates through 3 steps. First of all, you specify the number of clusters you want, k. That's number 1. Before the analysis even starts, we're like, all right, we want k equals 2, 3, 10, 20, whatever. All right? We assign their locations randomly or in specific locations, right? Randomly or in specific locations. You throw it into your data. The algorithm then, behind the scene, assigns all the observations in the data set to the nearest cluster. So basically what happens is each data point measures its distance to each one of the k center points, the k points, k center points. Whatever has the smallest distance, whatever data point is the closest to one of those k center points, it gets put into that center point's grouping, right? Into that grouping. Then the location of each cluster center is recalculated by calculating the mean of all the members of the cluster across all dimensions. What that basically means is, once we took that first step of creating, assigning each data point to a cluster, each central data point now has a cluster around it, right? That is assigned, it has all these data points assigned to it as a cluster. What we then do is we take all those data points assigned to that particular cluster, and using those data points, we move the central point again within that subset of data for each cluster. So for example, let's say we have 3 clusters. 3 data points are put randomly within the data, okay? Each data point is then assigned to one of those 3 central points. Now we have 3 groups. Within each of those 3 groups, we recalculate what the center point is just within those data elements. The central point will move. All right? Now that the central points have moved, we now again have each data see which new central point, because all the central points moved, is the closest. The groupings are redone. When the groupings are redone, a new central point is found again. This process happens over and over again until those center points within the groups stop moving. When they stop moving, the algorithm is done. And I bring up this algorithm because, yes, in your practice set, you guys know we're going to be programming this. Right now we have, obviously R does this behind the scenes for us, but we're going to be doing a crude version of this just so you guys get comfortable with the algorithm, a better understanding what's going on behind the scenes. It's basically step 2 and 3 that keeps repeating, right, until there's no further movement of the center point and the clusters. So basically, each data element, the central tendencies of those clusters don't move, and the data elements stop being assigned from one cluster to another. Now, this brings up a very, when you're doing k-means, a very interesting question. How do you know how many clusters to choose? Well, usually you're doing k-means because the business case drives that number. The particular business problem you're solving drives that number. Or the data, in some examples, in some situations, the data itself will help make that apparent. Right? We'll make that apparent. And now we can jump into today's first part of the lab. Right? We actually have two sub-labs within clustering. One for in the clustering lab, one for k-means and one for hierarchical. All right, so today's lab involves choosing locations for what we call 3 kiosks that are strategically placed. Well, 2 or 3. Let's say 2 or 3 kiosks that are strategically placed among the bike stations in our data set. The idea here is that people will work in these kiosks throughout the day, right, to help the riders with routes, sell small products and services to the riders, and for the tourists, basically, to help them sightsee, give them tips on sightseeing, and for the residents of the DC area to help convert them into actual annual members, right? In City Bike in the city, there's different types of membership. They have like a daily pass for tourists, a weekly pass for tourists, and then they have obviously monthly, quarterly, annual plans, and the annual plans they really like to sell for local residents of New York. Our job as data scientists, ladies and gentlemen, is to find the locations of those bike sharing stations provided in the data, to use the data to find where these bike stations should be, and recommend where to put the 3 kiosks, or maybe 2, even 2. We want to make sure that no bike sharing station obviously is too far from at least 1 kiosk. This is a great example of a project that dictates how many Ks should be in our clustering analysis, right? We're saying the use case from the businesses, from the Washington State, from the government is, listen, we want 2, possible 3 kiosks. Let us know, right? Give us a trade-off. Let us know which one we should do. Give us some recommendations. And as data scientists, we're going to have at it, right? Now we can get in it and jump in the data and start doing the analysis. All right. Just copy that. Open new file. And let's save it. Done. All right. I'll save my file into a file called bike. As you guys know, we always mess up with the data. Just in case, we'll do that. All right, done. We have latitude, we have longitude. Now, like I said before, all we have is latitude, longitude, they're numbers. We don't have to do anything in terms of categorical data. We're pretty much set there. Now, who remembers what latitude and longitude are? Which one refers to the x-axis of the map? Which one refers to the y-axis? This can get a little confusing. Longitude, even though it has the long in it, right, does not refer to the y-axis. Longitude are the points that go on the x-axis, as you can see here. Latitude are the points that go on the y-axis, right? Longitude is x, latitude is y. How do you know this from this point right here? Well, as you can see, the longitude are all negative numbers. Why are the longitude all negative numbers? Because the 0 axis, right, the 0 point on the x-axis on the global Earth world map is what we call the prime meridian. At the prime meridian, I think it separates somewhere in Greenwich, right, in Greenwich or Greenland or something like that, somewhere in Greenwich, England. I'm sorry, Greenwich, England, somewhere, right? So there's people in England that are in a longitude of positive or negative, depending where they are in the prime meridian. Okay? Now, latitude, here, that's why you'll see the longitude, it's all negative. Why? Because the west is all negative. The east, Asia, and all those places are all positive, their longitudes. Now, latitude, the latitude is positive. Why is the latitude positive? The latitude is positive because the number 0 on the y-axis of the world, on the world Earth or global map is, that's right, the equator. So everything north of the equator is positive, everything south of the equator is negative. And because DC and Washington, D.C. were both in the west and north of the equator, our longitude is negative, our latitude is positive, right? That's just a great refresher when reading maps. So we can check for nulls. I don't think we have any nulls in this data, but don't take my word for it. So if I simply just do command, as you see, integer 0, there's no NA values. We're good to go. Very simple data. We're ready to rock. All right. So first things first, let's get our graphing package out. Let's graph these data points, people. See what we're dealing with here. I'm going to simply do a scatter plot again, guys. A simple scatter plot. On my x-axis goes the longitude. On the y goes my latitude. And boom, boom, boom. You have all the bike stations in DC right there in front of you guys. And I don't know if you guys have ever been to DC or checked out a map of DC. There's a very nice outline. It gives a pretty nice outline of DC, Washington, D.C. Oh, very cool. All right, so running the k-means function. The k-means, the k-means function that does the algorithm we just discussed, and you guys will be writing yourself, is basically k-means. It's that easy. It's that easy, all right? So here, I'm going to write my k-means function. Now, when I do my k-means function obviously has, this algorithm has randomness behind the scenes, all right? And it's going to do it's going to take that iterative approach that we discussed before, that algorithm. It's going to do that for the closest k points, all right? And it's going to keep doing it until the points aren't moving anymore from one group to another. And it's doing it so it can reduce the average distance from the data points to those central k points. All right, but because there's randomness involved in this k-means function, I'm going to use the setSeed feature. Right? What does the setSeed do? I think we talked about this before. Set.seed, right? What set.seed does again, as a refresher, it's basically so that I can do my random analysis. For example, there's a function in R called sample. If I do sample, let's do 10. And what sample does is basically, there's a ton of random packages in R and Pandas and NumPy that take random numbers, right? So what does sample do? Sample basically takes a sampling of numbers. In this case, let's make it a little more advanced, right? So let's say I have 10 numbers, 1 through 10, and I want to get a random sample of 3 from any number from 1 to 10. I can just keep running this function, and it keeps giving me random numbers from 1 to 10, right? Cool, right? Randomness, very cool. Now, what does set seed do? Well, when you're doing analysis like we are doing that involves randomness, right? It can get pretty, if you want to test, you want the randomness, but when you're testing certain features of your algorithm or your analysis, you want the randomness to be the same set of numbers over and over again because you're testing a certain feature of your analysis, right? You're testing a certain feature of your analysis. That's the case with us, right? Even though we're doing k-means analysis, we want to be able to, in my case, because of the fact that I'll be running this analysis over and over again, I want to be able to recreate the same results for presentation purposes. So that's when I use set seed. You don't have to use set seed. I just do it more basically so I can keep my results the same as much as possible. So when you use set.seed, what happens is you can choose any number, and put it there within the parentheses. It does not matter. What that number dictates is basically that number becomes quote unquote the seed from which the random series of numbers gets generated, right? And what happens behind the scene is when we're running these random numbers, the seed itself is random itself. It's random itself. So in this case, let's say I choose 100. And then when I ran set seed as 100, and then I run any sample function, not just sample function, but any one of our random packages or random sample packages, it gives me the results 435. Now, if I run sample again, I get a completely different random number. If I go back here and I do set.seed 100 again, right? And then I run sample, I get 435. In fact, every time I do set seed 100 and then I run that sample, that particular line of sample, I get 435. You see that? That set.seed for a particular number locks in a particular order of random numbers that I generate. That's the logic behind it. That's the logic behind it. Without it, sample runs wild again, randomly, which is obviously in our analysis what we want. It's just for the sake of when you're doing a presentation of some sort or when you're learning something for the first time, you might want to lock down the variability of your random numbers. That's what setseed does. So that's basically what setseed is doing here. All right, so here I'm going to go do my k-means analysis. And look how easy this is, guys. All right, people make a big fuss of data mining, all this nonsense. And look how easy this is. First of all, we can do 100. And let me do my k-means. My first parameter is my data set. My second parameter is basically how many clusters I want in that data set. Boom. And now I have my k-means model. And you'll notice up here, K3 is what we call a list of 9 objects. What is a list again? A list is a special kind of data container in R. A special kind of data container in R, it's basically a data container for data containers. It's a data container for data containers. That's what basically it is. All right? So here, let's see what's in K3, right? When you've processed K3, you get all these results back. What are these results saying? Well, they're basically giving you a summary of the whole analysis, right? It's giving you a summary of the whole analysis, right? That's what K3 has. That K3 object basically has all the information after the analysis. This is kind of small. Let's just go here. Okay. So first of all, what does it give you? It tells you, hey, you got 3 clusters, obviously. We said we wanted 3 clusters, and it gives you the size of your 3 clusters. Now remember, we have 244 rows, and so those 244 rows are each a separate bike station. Each row is a separate the location of a bike station. And so it's basically saying how many bike stations are in each cluster. There's 93 in the first one, 102 in the second group, and 49 in the third one. And then another thing it gives you is cluster means. What are the cluster means? Those are those center points of these 3 clusters. Of the 3 clusters, these are the final center points of each cluster. And it's literally giving you the location of each of those center points. Now, ladies and gentlemen, what do these center points become in our analysis? Remember, what is our business case here? we were trying to find where should we set up these kiosks so that they are centrally located within our bike stations. These cluster points, these central points, are basically the center point of each cluster, right? Of each cluster. So what do these center points become? These automatically become our 3 locations of our 3 kiosks, right? That's how easy it was. We identified a center, we identified a location, 3 locations within our data that would be directly, that would be in the middle of 3 different groups, so that it is the minimum distance. Each bike station has a minimal distance to at least one of these kiosks. That's the logic behind it. All right. The clustering vector, what is this? This is basically, it goes row by row. I mean, this is a vector that coincides with the rows of observations right here in bike. And it basically is telling you which group each data point belongs to. So each one of your rows of data, each one of your bike stations in your table is identified as which group it belongs to. And this, like for example, the first row, the first bike station in the first location, the first row, it's been assigned to group 2. It's been assigned to group 2 because the center point of group 2 right here is the closest to it. Its distance from itself to this kiosk in this location is the closest, and for that reason it's in that group. This one, the second row, the second bike station, same thing. The third bike station, well, its location is actually closest to this kiosk, so it's been assigned to group 3 kiosk, and so on and so on and so on. Okay, and now here we have something called the error rate. Within cluster sum of squares by clusters, right? The between, first of all, the within sum of squares within one cluster, these are the what we call sum of square errors within each cluster. And this is the total on between the sum of squares versus the sum of the error of all the points to the overall central data point of all the data. Now this gives you a score of 65.6%. In a second, I'll be discussing what that is. The error rate, that's actually critical, pivotal to our analysis. And now here it's telling you all your available components. You have the clusters you can get, right? That's this, the clusters. You have the centers, longitude. You have these different errors that we will use to do our calculations within SS, between SS. And we'll go off basically in discussing what these error terms are and why they're pivotal to our analysis, pretty much. All right, we can, all these, we have access to all these components because these are list objects, and I'll show you how we have those. All right, now we had that error 6.63.2. All right, what is that? The 63.2 error is basically how well the model fits. The error is the ratio of the average sum of squares between each cluster and the mean, which is divided by the sum of squares for all of the data. Okay, so here, this is the numerator, and this is how we get the error rate. Between each cluster sum of squares, right, between the cluster sum of squares, divided by all the sum of squares for one center point. There's an overall center point, bam. There's all the center point, bam. And the sum of squares right here, right, if you guys remember the formula, the sum of squares, added up. So that would be the denominator. And the denominator, you would pretty much, the numerator is going to be the sum of squares within each cluster. Within each cluster. The idea here is we want the a lot of similarity again between each cluster. So we don't want that much. We don't want that much distance. We don't want that much error within each cluster. But we want maximum amount of distance from each cluster. So within the cluster, we want minimal amount of differences, And then between each cluster, we want maximum amount of differences. All right, maximum amount of differences. And this is why we want to maximize the error of the numerator, because the distance between the sum of squares in the numerator should be as high as possible, right? This is the reason why we want to maximize the error of the numerator, right? The numerator is basically, I mean, that's because the numerator is the error rate between basically the distances between the clusters, if you want to think about it like that, right? The distances between the clusters. We want the numerator to be as large as possible. The denominator is basically going to be the distance, the sum of squares between all points and the center point. And the idea here is that if each individual point was its own cluster, let's assume, for example, you had 5 data points, right? And each data point was its own cluster. So each data point is a cluster of 1, okay? In that example, if we took an extreme example like that, the error rate would be 100%. Why? Because first of all, if you have 5 data points, the denominator is fairly straightforward. It's going to be, you're going to find a central point for all 5 points, and you're going to measure the distance, the error distance between each data point, okay, between each data point. And that's sum of squares, right, using this formula right here. That's going to be the denominator, all right? If the numerator becomes, well, each data point is its own cluster, well, now the distance between each cluster is going to be the same thing as the denominator. And that error rate will be 100%. That error rate will be 100%, okay? And that error rate is basically telling you, oh yeah, 100%, fantastic. That yes, we maximize the distance between each cluster. We maximize the distance between each cluster. Well, in this example, we didn't really make any clusters. We kind of cheated each data. But that's basically what the error rate is telling you. So in this case, even though we call it an error rate, right, we want a high number. The higher the number, the more uniqueness among the clusters, the more distance there was among the clusters, the more distinction there was among the clusters, okay? The higher that error rate, the more distinction there was among the clusters. The lower that error rate, well, then that means that, hey, there's not much distance between these different clusters we created. Is there really a pattern of clusters around the data, right? Is it just a cloud of data points and there's no really discernible pattern? There's really no discernible there's really no discernible characteristic or characteristics that would lend itself to create subgroups within the data set, right? If you don't have a high error rate, that's what it's basically saying. That, hey, guys, there's no characteristics really in this data set that lend itself to making some sort of groups that are unique to one another. We're just randomly throwing these data points into clouds, into data points, right? And that's what that error rate is saying. So again, the error rate, we want this to be as high as possible. We want this to be higher. I don't know, again, why do they call it the error rate then? But they do, right? And you saw that right here, right? This term right here, when R gives you this, R probably gives you a more logical point. They don't really tell you what it means, but between divided by total, right? This number right here, 63.2%, that's our error rate for that analysis. So it's more than 50%. So it's good. It's not great. It's good, but not great. All right. We'll go with it. We'll roll with it. All right. Let's visualize the clusters, shall we? Let's visualize the clusters. All right. So look, we have these clusters already made. Let's check it out, shall we? Let's take our K3 cluster now, like before. If I do K3 $, notice, remember, our K3 object we created. If you do $, it's showing you all access to all the data elements within it. We want to go ahead and utilize, let me do it up here. Why am I doing it down there? We want to go ahead and utilize the cluster property, or the cluster data container within the list, within the K3 object. And it gives you literally the positioning of each one of the clusters. I'm going to go ahead and copy and paste. Scooch that over a little bit. All right. And the first thing I'm going to do is, actually, I don't need to do that. Boom. Boom. All right. So here, guys, I'm going to create a new column called cluster3 for my grade 3. All right, you know what? Let me call this. Yeah, fine, cluster. Let's keep it consistent with the slides. Right, boom. And basically all I did here, guys, I created a new column called cluster3. And sorry, if I type in bike here, you notice I made a new column called cluster3. And now each bike station now has its assignment of which kiosk, either kiosk 1, 2, or 3, is closest to it. All right, and now we can visualize it. Boom. And just like before with our Titanic data, we can basically discern the colors based on the clusters. Now, notice that we have a range of colors here. You can see the light blue, the medium blue, and the dark blue. We have a range of colors over here, right? Why do we have a range of colors? Well, because cluster3 is, right, it's a numerical column or a categorical column. Is it nominal or is it ordinal? Right? This is the result of not properly identifying your column that we just created. All right, if I go str bike, all right, cluster3 is considered an integer, but remember, is that really an integer or is that a categorical column, guys? Okay, is that really an integer or is that a categorical column? That's a categorical column. Cluster3 is a categorical column. It's basically saying, hey, this bike station belongs to this. This kiosk is closest to it. These numbers represent the kiosk that is closest to the bike station, right? It's a categorical column. Is it nominal or ordinal? It is ordinal because these are just the 1, 2, and 3 are just labels for the kiosks. Each kiosk is not greater or lesser than the other kiosk. It's just a unique identifier for each kiosk. So how do we deal with this? That's right. We're going to do a factor game. Cluster3. Sorry. Cluster3. And that's it. Oops, forgot my bars. And that's it. It's that straightforward. It's that simple. All right, now let's run this graph back. Now that the data is categorical, boom, you see the difference. You see the difference in the graph. There's now look at the key scale. The key scale is now at a range. It's discrete colors and numbers, different colors and numbers, and you see, look at why it did that. Why it did that? It's because now it's categorical. See, a numerical graph, if we use the numerical column as for the colors, those numericals aren't distinct numbers. They're considered, continuous numbers. So it gives you a scale of colors. It gives you a scale of numbers that, sorry. So it gives you a scale of numbers so that you can see basically how the colors should basically be, right? I mean, for numerical it does that. For categorical colors, it just gives you pretty much the blue, green, red, or it gives you distinct colors. So you can see the difference visually right there. Right, visually you can see it right there. All right, so let's do this. So here you can see now how the data points were broken out between each of the kiosks, right there, boom, boom, boom. Okay, boom, boom, boom. We can see that. This is kiosk 3. This is kiosk 2. This is kiosk 1. The colors are defined right there. And again, your map when you did this is going to be slightly different than mine because, again, there's a random factor when we're using k-means. There's a random factor. But notice how it broke it up. Okay? And that's basically what we want, right? So, obviously our center point is going to be here, here, and here. All right, and let's show that. Let's show that. So here now, K3 centers. K3 centers now gives us the locations of our center points. Notice it gives it to us in a unique kind of table looking thing. Is this a table? What is this? If I run str on it is a number, right? It's a number, 1 to 3 columns, 1 to 2 columns. What is this base? This is a matrix, right? What is this? This is basically a matrix, guys. That's what's going on here. All right, so that's fine. We can put a matrix directly. This is a matrix basically, and they give a matrix with column labels and row labels, and that's fine. We can put that directly into a data table. That's not a problem. All right. So if I use class here, that will tell you that. See, it's a matrix. It's a matrix. I don't show you guys matrices that much because we deal with data tables all the time, right? But in this case, it's not a problem. We can convert a matrix easily to a data table, so no worries, right? It acts just like a table, right? It takes 2 coordinates, a row coordinate and a column coordinate. That's all it pretty much takes. So 1, 1 is literally the first position, the first row, the first column, right? The first row, first column. Let's go ahead and create a table out of it. We'll call this the center. I said center DT. We should basically say center DT3. In my program, I'll call this center DT3 to differentiate between the center points for a kiosk analysis of 3 center points versus 2 center points. Okay. So I'll call this D3T, and this is be slightly different than my syntax here in my slides. I run this, and now you see cent DT3. Ta-da! This is a data table now. Okay? And now it's all the features and the functionality of our data table. All right. Now what we want to do is we want to add these locations, these center points, to our what? We want to add them to our map that we're working on. The map that we're working on. We want to add it to the map that we're working on. All right. So let's go ahead and do that. How do we do this? Well, I'm going to copy this, and then I'll show you. Oops. It's disgusting. All right, so the first point, that's easy, right? The GM point. Right, this first part right here, this is from our original graph. If I simply just highlight this and run it, we have our graph right here. Okay, now like I said before, the way ggplot works in layers in the language of exploratory data analysis. To this now we want to add additional points. So here we go. I now do plus. I now say, hey, I got additional points I want to add. I use the GM point. And now I put additional functionality within the parentheses. Here I have no additional functionality. It's getting it all from the main function. But here it's going to have a lot more functionality. Why? Because first off, we're putting on points from a completely different data table. Not the default data table, but a different data table, right? The cent, in this case, cent DT3 data table. So the first keyword I add is data within the parentheses. Data basically saying, okay, I'm using a new table to put these points in. Fine. Data equals cent D3. Done. Comma. I have the aesthetics in the ggplot over here. This is going to have different aesthetics now. I'm going to use, I mean, it's the same one pretty much, but I'm going to have this one based on this table. So even though it's like the same thing minus the color, I'm putting this aesthetics directly in the GM point. I'm choosing, this you've seen before, I'm choosing the colors, explicitly the colors to be something different. Okay. And this is something else I'm doing over here. You guys haven't seen this before. I'm saying, look, make the shape something called 11, basically a different shape altogether, and make the size 2 something bigger. All right, why am I doing that? I want it to be purple and distinct from the green, blue, and red data points. Because again, these are the locations of our hypothetical kiosks that are going to be in the center of these bike stations. I go ahead and I run this, right? And look what you see. That's the bike shape. That shape 11 is this weird star thingy right here. Boom, boom, boom. We have our kiosk. So visually now you can show your clients, hey, here's the logical breakup of your bike stations, right? Logistically. Here, if we have 3 kiosks, this is technically where those kiosks should be, so it minimizes the distance for every bike station. So no bike station is too far from one kiosk. Even ones that are over out here on the border, it has this one close to it. Here, or here. Within these center points, you have different kiosks that are close to it within these center points. All right, and this is how you visually show your clients what's going on, and more importantly for yourself, for analysis, for a visual point of view. All right, and there we visualize the stations. By the way, if you want to change the shapes, I put a little table here for you guys, so you can see the different shapes that you want. I used the 11 one right here, which was that little star thingy. But we can use something else if you want to use, I don't know, this upside down triangle. That's number 6. We'll throw number 6 in there. It has more like a Superman feel to it. All right. And these will point out your bike stations. Cool? All right. Now, what if we decide on 2 stations? What if we have a situation like that? We decide on 2 stations. What are we going to do now in that situation? Well, look, that's not a problem. That is not a problem. We could rerun the analysis for 2 stations. In fact, when you're doing analysis, when you're doing projects like this and you're working with different people, you're going to run a situation like that. The what if scenarios. Okay? So in this case, not a problem. All right, that's how it looks like for 3 kiosks, because remember, cost is a factor. Every time you build a kiosk, you're spending money, right? You're spending money on these projects. So we're saying, all right, instead of 3, let's say we did 2. 2 stations. No problem. I'm going to rerun my analysis, except instead of for 3, I'll do it for 2. Now be careful when you run this analysis this time. When we ran it the first time for K3, bike had just 2 columns. If you look at bike right now, it has 3 columns. K-means will give you some weird results because it's going to do clustering analysis based on this column, and that column. 3 attributes instead of just 2. So when we do our K2 analysis, right, we're doing it for all the rows, but just the latitude and the longitude columns. All right. And instead of 3 clusters, we want now 2. Let me set my seed to 100 like I did last time. Keep things consistent. Boom, boom. I got my K2 analysis, right? And I'll run it back. I'll run everything back again. Do you want to see it? Let's see it. So just like before, I'm now going to have a +2 column, right? And just like before, if you want to visualize it, oops, we gotta put that in first, genius. +2, K2 clusters, excellent. Now I can factorize it. And now I'll create my, this is what I was saying before, I'll call this cent dt3 to differentiate it from this one now, cent dt2, the centers, and now cent d2. So now let's check it out. Bike now has my cluster 3 and cluster 2 columns. The cluster 2 column is now, hypothetically, if we had 2 kiosks, where each one of those bike stations would be closest to, what kiosk would be closest to it. And the cent d2 table is now going to be the center point for those 2 kiosks in a 2 kiosk scenario. So here I have all this, and now let's graph it. I'm going to cheat, take this, what I did right here, copy it. First of all, real quick, let me run K2 right here. I just wanted to show you guys that, look, in K2, when you have 2 kiosks, look at what happened to my error rate. It went down to 63 to 53.4%. Not good, not good in terms of distinctions. Right, just wanted to point that out. But anyway, continuing on with our analysis, I'm going to make these points based on +2. So if I do this, you have the 2 distinct locations now. As we can see, what happened was one of the locations became merged. The kiosk that would have been in the 3rd section got merged into the other 2 kiosks, right? Which kind of makes sense. Again, depending on your randomness, your graph could be slightly different than mine. All right, and so now if we do it for everything right here, instead of cent d3, we do cent d2. All right, and there you go. And if we just want 2 kiosks, this is how it would basically look like. Does this make sense? This is where the 2 kiosks will go. This is where the 2 kiosks will go. All right. So what is this basically setting up for? Well, like we said, what if we decided on 2 stations? Well, how much of a difference was it in terms of those 2 stations? Like, how much do those 2 stations cause movement within our 3 kiosks? So if we had 3 kiosk stations and then we decided on, instead of 2 kiosk stations, how much further was those stations from one another? Well, no problem. We can lay the other, and this is the beauty of, so you see how I just asked that question? How far was the distance from the 2 kiosk locations to the 3 kiosk locations? I asked a question. That question I can ask directly in ggplot. That's why we have this funky lingo. That's why we have this funky syntax. Right? That's basically the way it works. Boom. I just put that layer on here. I literally take that line, cent dt3, color purple. Now here, let's choose 3 different points. So I have shape 6 for the 3 kiosks. For shape 2, let me use, I think in my notes I use a black dot. Let me use I already have a circle up there. Those are circles. I guess let me use this number 12. Those 4-point boxes, number 12. So for cent D3, I'll use the Superman symbol, upside triangle. For this, I will use 12. Oh, let me use a different color. So that's color purple. I'm going to use color blue. That's not that distinct. Pink, purple. I don't know why I'm thinking about colors all of a sudden. All right, whatever. This should be fine. Let's do black. I think my notes I do black. That's slightly more different. Okay. And boom. There you go. Right there you see it. The upside down triangle, Superman symbol, is basically showing you where your three kiosks would be if we built 3 kiosks. That little square, 4 square black thingy is showing you where your 2 kiosks would be if we only had 2 kiosks. So here we see there's not much of a difference between this point and that point. Actually, within our graph, it doesn't look like it's that much of a difference. Again, it depends on the dimension of your graph, right? But here, visually, it does not look like, because they're within its own box, these are that far from one another, these kiosks, right? Here, you see the difference. These 2 kiosks actually collapsed into this one kiosk right here. That's basically what happened. These 2 kiosks, which look like they're a bit further from the center point, collapsed into this one center point over here. That's basically what happened. Whereas here, the location didn't move as much. This location didn't move as much. All right. Now, why does this matter? Why are we even talking about this? It's because, right, most of the time these projects, they want to do it, especially when we're talking about infrastructure like this, they want to do it in an iterative, sequential process. They might want those 3 kiosks, right? But for budgetary purposes, and this happens all the time, they'll be like, let's build a couple first. Let's build 2. See how well those kiosks do for generation, from in terms of their intended purposes. To sell to tourists, help tourists. In other words, promote tourism, and at the same time converting the permanent residents into annual members. Right? It's a budgetary thing. If it's working, we'll jump on and open, new kiosks. That's basically what New York City did with those bike stations. They started off with the most dense locations where people are moving, and they're like, let's start with these locations, see how many people sign up, see how it goes, and then they just rapidly went out from there, right? They had a central plan. Bloomberg had a plan, and he's like, let's do this in a sequential order, in different stages. All right, so before we do that, remember, we can go ahead and show our graphs based on the different clusters, basically where each bank would go. So here, basically, I'm adding the facet wrap to our graph, and basically, I'm saying, hey, let's show this graph like this. Basically, what I did was here, instead of cluster 3, do it by cluster 2, do it by cluster 3. So now what I have my 3 groups. I have my central locations for the 3 kiosks. I have my central location if we do 2 kiosks. And we could take this one step further. You could throw in facet wrap, and I can make 2 graphs side by side. Based off the cluster 2 categorization. And now basically what I have here is cool. I have so side by side I have, look, cluster 1. If I had, so these 2 boxes basically represent if we did 2 kiosks. And it's basically showing, hey, this is cluster 1. This is showing cluster 2. But within each graph now is showing where the 3 kiosks, how the 3 kiosks would, if there were 3 kiosks, where those bike stations would be split up. And as we can see, why is this important? Why am I doing this analysis? Well, I gave you the situation where, let's say we want to do sequential building. We want to do 2 kiosks and then 3 kiosks. The question is, if we're going to build 3 kiosks, right? Which 2 kiosks do we build first? And so what this visually is showing you that if you do build, if we do build 2 kiosks and then 3 kiosks, well, in the 2 kiosk analysis, we're basically saying, it's not that many. It's not that many of the second. So let's say that if we have 3 kiosks, the 3 kiosks, there's one set of bike stations that look like it pretty much, whether there's 1 kiosk or 2 kiosks, this kiosk would pretty much be built in this area right here, right? Because when we have 3 kiosks, there's not that many more bike stations added to this group. That's what this green is showing here. That's basically what this graph is showing you. This graph is showing you that when it goes from 2 kiosks to 3 or 3 kiosks to 2, how those bike stations get reallocated to each group, right? So this group over here, the group 2 in the green right here, this really gets merged into this group right here for the most part, right? Some of the bike stations go into this group, but most of the time it's this, as these 2 groups will get merged into one. That's basically what happens. And that's why these 2 kiosks right here get merged into this point right here. And this one right here barely moves up a blip. That's basically what's happening here. That's what it's showing. All right, it's really good to, from a visual point of view, it's kind of good to know that, oh, you know what, so from a visual point of view, what I'm saying is it probably makes sense to me, right? And again, we'll quantitatively prove this. Quantitatively, we might get a different answer, but from a visual point of view, if the company says to me, if my clients say, you know what, we want to build 3, but we want to build the first 2 first, which first 2 should we build? I would say, look, you're going to build this one. Why don't you go ahead and build this one right here, right? Because it's not very far from if you were to have 2 kiosks anyway. So why don't you build this, definitely why don't you build this one here, and then we'll decide build one of these ones right here, the first go around. Perhaps it makes sense to build out this one right here, the further one, and then save the middle one for later, right? So that's basically from like an ideas point of view, it would basically throw that out. Well, let's go at it and figure that out quantitatively. All right, business case, 3 scenarios. Business case, the 3 scenarios. We want to analyze 3 scenarios. The 3 kiosk plan, the 2 kiosk plan, and a two-step process where 2 of the 3 kiosks are built first, and then a third kiosk is built. This leads to 2 questions. Which 2 kiosks should be built first for the last part? And what is the average added distance for each bike station? All right. The answer to both questions rely on converting the longitude and latitude coordinates to actual distances, right? To actual distances. We need actual distances between these points. To do this, we are going to use a package called Geosphere, right? Now look, there's a cool algorithm that does this for you, right? We're not even going to worry about the algorithm because, damn it, we're R programmers. And we have a package that does this for us called Geosphere. We're going to install Geosphere just like we install those other packages. And Geosphere is basically going to help convert the distances into miles. Why do we want to do this? It's because we want to present our 3 scenarios to our clients. And the basics, like when you're doing an analysis like this, not only do you want to visually show where these points would be, but what they care about basically is, how far is the closest on average? Like on average, show me how far the distance is between each bike station and each kiosk, given my 3 different scenarios, whether we do 3 kiosks, 2 kiosks, or a 2-stage plan from 2 to 3. What would be my minimum distance, average minimum distance? What's my minimum distance? What's my maximum distance, right? Show me these analytics. Let's make a decision, right? There's going to be pros and cons to each plan, and let's make the decision. All right. Now, to do this, though, we got to convert these distances to, these locations on a map to distances. All right. So let's go ahead and load this up. I already have Geosphere, guys. You guys need it, so go to Packages, go to Install, type in Geosphere. Is that it? All right, type it in there. It should fill it in. I don't know why it's not filling it in. Oh, here we go, finally. Boom. All right, install it. I already have it. Once you install it, call it. Boom, that easy. All right. Now, we're going to do this simple example right here, guys. Simple example, right? Okay, that's how you use the function. Now, scroll this over so you can see it fully. All right. So if you notice, the first parameter is a vector of 2 coordinates. Again, you have your latitude, longitude, latitude, longitude. It doesn't really matter which order you give it in. What matters is when you're comparing the distance of 2 points, you are consistent between your which one's the latitude and which one's the longitude in order, right? That's all that matters, okay? So my first parameter is 0.1. My second parameter is 0.2. And my third parameter, fun, stands for function equals distance Haversine. Distant Haversine. This is a particular algorithm for figuring out the distance, the curvature distance between 2 points. I'll explain that. I'll talk about that in a second. I run this. I do dd. And what does dd give me? It gives me this value, 33,713. Right? What does that mean? All right? What does that mean? And by the way, first of all, notice that the value comes back as a, look at that. It's not a number. It's a matrix. It's a matrix. All right? It's a matrix. Just throwing that out. All right. Even if it's just 1 point, it gives back as a one point matrix, 1 row, 1 column. All right. Let's talk about this. All right. Now, what is distant Haversine? All right. It is a mathematical methodology. There's a couple different mathematical methodologies out there for calculating distances on using longitude and latitude. Because remember, longitude and latitude, it's points on our Earth, and our Earth is basically a sphere of some sort. It's a sphere of some sort, right? So this distant Haversine, it's basically an algorithm that assumes a spherical Earth, ignoring ellipsoidal effects. What are ellipsoidal effects? You guys, I don't know how much you guys know about astronomy, but our Earth is not a perfect ball. It actually is the way it spins. Any kind of in physics, when a ball spins, the rotation, right? So if it's rotating, let's say around my finger, right, the center point, the vertical center point of the rotation, the equator, if you will, gets slightly larger than a normal sphere, when it's in rotation. It's on rotation. For my cricket students, my students that follow cricket, when that ball is rotating, when you're spinning that ball, the direction of the spin, the center point of the ball gets slightly larger. That doesn't happen when the ball is a new ball because it's hard and it has that ridge underneath it. But that'll start to happen when the ball gets older and those spins start happening, right? And then, you have people like Wasim Akram can start doing weird things with it, right? Last grade probably cricketer for bowler for Pakistan. But anyway, so this particular mathematical methodology was made by this guy named R.W. Sinnott in 1984. But I mean, he formalized it in equations, but it was actually being used back much, much longer than that, right? By ship navigators and all those people. They just assumed this perfect sphere. They didn't take into account any ellipsis or ellipsoidal effects of the Earth. All right, so that's why we do it. It's very simple. It's a very simple algorithm, and it's perfect for us. We don't need that level of we don't need that level of detail that we need to have to take into the ellipsoidal effects of the Earth to get this analysis. All right, now there's a slight problem. 33,713.61. The result is coming back as in kilometers. Kilometers. This be America, people. We don't use kilometers. All right? We use miles. You do a presentation to some good old Americans, right? And talk about kilometers. They're gonna be looking at each other like, is that bad? Is that what is that? We don't. How many football fields are we talking here, right? We gotta convert that over to miles, people. All right. To address this kilometer debacle, right? We will apply a simple mathematical trick. We'll simply divide our results by 1609, right? By dividing by 1609, it converts the distances from kilometers to miles. All right, real easy. So here, if I just rerun that back, let's run that analysis back, and this time let's run that analysis back so that it's done for human beings. Kilometers. Huh. This is a great example of where the world is wrong and America's right. Boom. All right, there we go. So the distance between those 2 points is 20 miles. 20 miles. All right, 20 miles. There we go. There's something that your client can understand. Kilometers. Huh. All right, so let's go ahead and do this for our analysis. Let's do it for our step-by-step plan. Okay. So what I want to do first is I want to let's knock it out let's do it for our 3-step kiosk plan first. All right. For a 3-step plan, let's go ahead and find the distances from each kiosk to the center point of each of those. For each of the bike station to the each one of the potential three kiosks. Each potential 3 kiosks, right? We obviously know which kiosk is closest to us because we have that in our data. But nevertheless, let's just construct the miles. We need it anywhere for future analysis, right? Now look what's going to happen here, guys. Let me copy this. All right. So look what's going to happen. First of all, I'm doing this send dt3, right? I'm using my other table. So I'm giving it, my first parameter is the whole table, not 1 point, the whole table, just the latitude and longitude. And my second one table is sent D3. Let me just make sure that this is in the right order as well. Yes, latitude and longitude. Notice okay, excellent. Latitude, longitude as well. So it's in the same order. This is a table of results. It's not 1 data point. This is 3 points. This is going to be 244 points. This is going to be 3 points. And then everything else is the same. What's going to happen with our result matrix? No problem. Let me call this, by the way, result matrix 3. So differentiate between our 2 analysis and our 3 analysis. We have a bunch of warnings. It's okay. It's all right. Don't worry about it. All right? Warnings are all right. Errors is what we care about. So when I run this, look what I see now. See, before when I ran it for just 1 point, I got just one answer. I just got one answer. But now that I ran it with one table to another table, right, I got a matrix of results back. Let's explore what's happening. The first row gives us 3 results. Why does it give us 3 results? Well, what happens here is it's comparing the first location of the first row here to the 3 locations in this table. And those distances are right here. The first, right, the second, the third, because there's 3 points here and sent dt3. So this is the distance from here to here. This is from basically the first bike station. This is the distance between the first bike station and the first kiosk, the first bike station and the second kiosk, the first bike station and the third kiosk. What's going on here? Well, this is the distance between the second bike station and the first kiosk. That's what the 2 here is. Second bike station and the second kiosk. Second bike station and the third kiosk. The distance here is the third bike station and the first kiosk. Third bike station and the second kiosk. third station, bike station, and third kiosk, and so on, so on, so on. It gives us the matrix results back. Real easy. And it gives it to us in miles. All right, so this is a good spot to end this video, and we'll pick up the second video right from this point. All right, so goodbye, everybody. I'll see you on the second video, part B of the video.